versus volume diagram, what we do, we start from a very high pressure where we know the system, the pure substance is in the liquid phase. And then by slightly increasing the volume, we'll see the huge change in the pressure. Okay, so the pressure drops. So we increase the volume till the first gas bubble comes out of the liquid. That's basically our bubble point pressure. Okay, and then after we hit the bubble point pressure, if we continue increasing the volume or the specific volume, what happens, the pressure stays the same, but more liquid converts to the gas. So the liquid converts to the gas as we increasing the volume while the pressure is constant. This behavior continues till we convert the last droplet of the liquid to the gas, and that's our dew point. And after that, since we have all the gas phase, you increase the volume of the gas pressure drops. Okay, so this is a very typical behavior of the pure substances. And actually, this becomes our lab number one. Where in our lab number one, what we are going to do, we are going to have a pure component like Cu2, and then we are going to study the behavior of pressure versus volume of the CO2 at different temperatures. Okay, so we try to collect some points where we have the liquid CO2 as we increase the volume, a couple of points where we have the two phases of the liquid and gas CO2 coexisting, and a couple of points where we have all the gas. And then we can generate this pressure versus volume diagram of CO2 at a specific temperature. And then we repeat this, at different temperatures. When we repeat this at different temperatures, for every temperature we can have this bubble point pressures and the dew point pressures and the vapor pressure lines. When we completed that, when we measured this at different pressures, we can connect all the bubble points, which then that line, which basically connects all the bubble points, is called bubble point line. We can connect all the dew points to generate the dew point line. And then when we extrapolate that, these two lines, the bubble point line and dew point lines, they meet at a point which is basically the critical point of the system. Okay, and then this area between the bubble point line and dew point line and the critical point is basically a region where we can have two phases of gas and liquid coexisting. Okay, to the left hand side of the critical point, we will have all liquid. To the right hand side, we will have all gas, and in between we will have gas and liquid. Okay, so this is how we generate the two-phase region for pure substances. Again, for pure substances, the property is when we drop the pressure, when we increase the volume and drop the pressure and hit the bubble point, the pressure will stay constant all the way till we convert all the liquid to the gas. So all the way here we have gas and liquid coexisting, and right at this point when we convert all the liquid to the gas, then we will have all gas. So to the right hand side of the critical point, so if this is a critical point and I draw a line here, to the right hand side I will have all gas, to the left hand side I will have all liquid, and in between I will have gas and liquid coexisting. Okay, so the point at which the first few molecules leave the liquid and form a small bubble of gas is called bubble point pressure. The point at which the small drop of liquid remains in the gas is known as dew point. And on the PV diagram, these 2 points are indicated by the sharp changes in the slope along the isotherm. Okay? For pure substances, as we said, the pressure at the bubble point and dew point is equal to the vapor pressure of the substance that can be obtained using the Cox chart. Okay, so if we bring this pressure versus temperature and pressure versus volume together, we can have the pressure, volume, and temperature behavior of a pure substance at any pressure, volume, and temperature condition. Okay, that basically defines the phase behavior of a pure substance at different conditions. Okay, so the things to remember from the first part of the lecture is the behavior of the pure substances, the critical temperature and critical pressure definition for pure substances, the vapor pressure line, the application of Cox chart, and then the behavior of the pure substances when you hit the bubble point, which basically the bubble point pressure will stay constant all the way to the dew point pressure, and that's equal to the vapor pressure that can be obtained from the Cox chart. Okay. So in addition to the pressure versus temperature and pressure versus volume, sometimes we are also looking at the density versus temperature. Okay. This is also a very good graph. We will review this graph again at the end of the semester when we are talking about the interfacial tensions. Okay. So what this graph is, so in this graph, we can do some experiment. We can measure the gas density and liquid density of a pure substance at a specific temperature. Okay. So at a specific temperature, we can measure what is the density of the gas and what is the density of the liquid phase. Okay. And then if we plot these, it turns out the average of the density of gas and liquid at a specific temperature falls on a straight line, which is a mean density line, and that straight line passes to the critical point. Okay, so we can use this to find the density at the critical point. So generally what you will have a table which tells you at a specific temperature what is the gas density and what is the liquid density. So if you plot the density of the gas as a function of temperature, you will get this part of the graph. And if you plot the density of the liquid as a function of temperature, you will get this part of the graph. Then at every temperature, if you average the gas and liquid density, it falls on a mean density line. So you just need to average 2 points, average the gas and liquid density of a pure substance at 2 different temperatures, then you will have 2 different points on this mean density line. You have 2 points on a line, you can write the equation of the line. We know the critical temperature of a pure substances. These are fixed constant numbers given at the end of the book. So for that temperature, we can find what is the density of the pure substance at a specific critical temperature. So you will have an example on your homework assignment which basically works with this graph. So what you need to do is, again, as I said, plot the density of the gas as a function of temperature, density of liquid as a function of temperature, and generate this density versus temperature diagram. Take the average of the gas and liquid densities at 2 different temperatures, and then draw this straight line, write the equation, and then read the density at the critical point of the pure substance. Okay, so this basically wraps up the phase behavior of the single components. So in the case of single component, we need to know the critical temperature, critical pressure, bubble point pressure, dew point pressure, vapor pressure, Cox chart, the behavior of pressure versus temperature, pressure versus volume, and density versus temperature. So these are the most important parts that we need to remember. We are going to use these from now till end of the semester. So it's very important to understand these concepts and go over it. And if you have any question, just let me know, send me an email, and then we can discuss that in more details. Okay. But now that we understand the behavior of the single component, we can move on into the 2 component mixtures. Okay. Because we know in the case of oil and gas, as we showed, in a lesson 1, chapter 1, the gas sample that we're getting from any gas well has multiple components, multiple hydrocarbon and non-hydrocarbon components. So we are not always dealing with the pure substances. But to learn this behavior, we needed to start with the pure substances and then make the system more complicated as we go forward. So the difference in the mixture behavior when we go from a single component to the two components, mixture of 2 components, is very significant. As we can see in the pressure temperature diagram or into the phase diagram. So this phase diagram doesn't have anything similar to the phase diagram of the pure components. If you remember, in the case of pure components, the region that we had the 2 phase was a line or a curve. However, if you have a mixture of 2 components, I will have a region area that I can have the two phase. Okay. And also the definitions would be different. If you remember, we said the critical temperature, so this is a critical point and this is a critical temperature. The critical temperature for in the pure component case was the temperature above which we couldn't liquefy gas. However, at any temperature here, which is above the critical temperature, we do have gas and liquid. Okay, so we can convert the gas to liquid. So if we just have a mixture of components, then that's very doable. And also the critical pressure in the case of pure component was defined as a pressure above which we cannot have gas and liquid coexisting. But here, for example, we know here we have a pressure which is larger than the pressure at the critical point, and still we have the two phase. So those definitions were only valid for the pure components. When we come to the mixture of two components, those definitions are not valid anymore. Okay. So in the case of two components, the critical temperature is simply the temperature of the critical point. Okay, and the critical pressure is the pressure of the critical point. Okay, we will use these critical temperature and critical pressures, but they will not have the same definition. So how do we generate these phase diagrams for the two components? We know if I have a component A, pure component A, then I could have a line representing the vapor pressure, liquid phase, gas phase, and then region above the critical point. If I have a heavier component, then I can have a line or curve that defines the vapor pressure of component B. So here I'm mixing the component A and component B, which are definitely different in terms of their molecular weight, okay? Because this one has a smaller critical temperature, this one has a larger critical temperature, and basically these define that these two components are different in terms of their molecular weight. So now if I start mixing these two, depending on how much of component A has been mixed with how much of component B, this two-phase region could be closer to the vapor pressure line of component A or closer to the vapor pressure of the component B. For example, if I use 90% of component A and only 10% of component B, this phase envelope will be very close to vapor pressure of component A. This phase envelope could be for a case where you have, let's say, 70% of component A and only 30% of component B. Okay, so therefore the whole phase envelope kind of shift to the left, closer to the vapor pressure line of component A. And if I have, let's say, 90% of component B and only 10% of component A, then this phase envelope will lay down and it goes somewhere here, very close to the phase envelope of the component B. Okay, so this is the behavior. Depending on how much of which component we add, this phase envelope will shift toward left or toward right. The other observation is, if you see the critical pressure of component A and critical pressure of component B, if we mix these two, the critical pressure of mixture is much higher than the critical pressure of component A and component B. So if critical pressure of component A is 200 psi and component B is 150, if I mix those, the critical pressure of mixture is somewhere around 400. Okay, so the critical pressure of a mixture is much higher than the critical pressure of every one of those single components. Okay, and as the difference between the molecular weights of component A and B increases, then this envelope becomes larger and larger as well. Okay.